Okay, now let us do a problem. This color thing unfortunately is not come out well. Each color was supposed to be 4, but so sum A star B. So we are doing for 1D array. So how do I sum? So multiplication is easy, right? Multiplication will be thread by thread and is highly parallel. So please remember that is AI star BI, then sum over all I, that is what I want. So element by element multiplication will be fast because there are as many threads as the numbers. Okay. So boom, in one shot it will be done. But how do I sum? Because this thread will say I do not know what you have done, I can't talk to you, so what should I do? So go to the shared memory. So the product you can put in shared memory. This is, in fact, I will say that I put a CI. Now CI is in shared memory for each block. Okay. So each block has shared memory, and these blocks will sum it up, do a local sum, and then these blocks will, well, this local sum will be managed by one of them, which will do global sum, and the global sum will be stored in global memory. So global sum has to be beyond shared memory, because it is global for everyone. So that is what is done. Thread wise I compute temp I, is not CI, I just put a temp I, and a temp I shared across threads within the block. And then sync thread, another important thing. Why should I sync it? Because it is possible all of them have finished their work. If somebody has not finished the work, one of the temp array may be 0, it is not got the right value. So you have to make sure that all of them have finished their work. Now I can sum, do the local sum. Please keep in mind that the threads are running in parallel. There is no loop, there is no, they are all independent. Okay. So we need to sync. So your code, so that is the difference. In MPI we are thinking of how each processor is handling data, okay, and each processor handling lot of data, but now we are thinking of how each thread is handling its data. So you have to just think differently for different ways of parallelization. So local sum will be summing the threads, is done by thread 0, where in the code which I am going to show you, and sum it, sum local. Okay, so it's clear. I mean, so this is a it's not a loop. There is no global variable. Well, there is global variable, but you have to define yourself in some ways. And sum has to be atomic operation. Why sum should be atomic operation? You all know what is atomic operation. We did that for OpenMP. In shared memory, this is my sum variable. Okay. Well, I should not put sum inside. Sum is name of the variable is sum. So it is 50. Then somebody comes and updates it to 75. But imagine that two of these blocks are trying to update simultaneously. Okay, there will be there is a register where you want to, two students want to write sign simultaneously, not possible, no, one at a time. So this is atomic operation is one at a time. So that basically when one person is doing it, the room is locked. We use lock for multi-threading. So same thing is done here internally. So you just say atomic sum, then it will atomic add, I think atomic add, and it will be done. So you do not have to create a lock and release lock, all that is not required, but when in shared memory, when you have to make sure that two guys are not doing things together simultaneously. So let us look at the code. This is the code function. This is our GPU function. So, dot product kernel. So, this is a nice thing to write kernel, so that it is, we know that it is running on GPU. It has 3 arguments, actually it has only 2 arguments, no sorry 3 arguments, we need C. So, AB is AB are arrays, these 2 are arrays, and this is the global sum. I should have used variable sum or something, some different variable, but unfortunately I use the same C. Okay, so, we create a shared array, shared variable. So, the syntax is, these are double line, double underscore, 2 underscore. Okay. These are keywords, very special words. So, that says that whatever I am going to declare now is going to be shared variable. It happens to be a array, its size is thread per block. I have defined it before. So, number of threads per block. In this picture, if you look at the color, it is 3, it should be supposed to be 4, but it is 3 according to color. Okay. So, this will be shared by threads within the block. Okay. Now, it is integer type. Now, after that I need to get the index of the global index. Okay. Actually, I do not need this, yeah, so yeah, that is right. All right. So, this is the, so by the way, each thread knows which block it is in and which thread it is in. Okay. So, here I am putting the number, this is shared memory. Okay. So, I am putting A star B, so it is a global array values I am multiplying and putting it in temp. So, it is said C I equal to, or temp I equal to A I star B I, but this temp, if I put I, then temp will be a global variable. We do not want that. I want to store locally. So, that is why I have thread index. Okay. Is that clear? I think even this the thread index may work if I put thread index, because it is a local A. But anyway, this code works. So, it is using the global index, but it is doing inside the block. It is not taking memory from outside. So, it is A index and B index. So, it is looking at global index of A and is plugging it, multiplying and putting in temp, is putting it here. You can check this code by just putting thread index here, because each guy has unique thread index, and that should work, and sync thread. So, now temp has been created, which has, each guy has its own A star B. Now, I am going to do the sum. So, who is going to do the sum? Thread index 0 for each block. Okay, now, this is what we need to, each block. So, this is run by everybody. So, then it says, well, who has thread index 0? So, how many thread index 0 will be there for 4 blocks? 4 of them, and those guys will say, well, now you are assigned to do this work. Well, nobody is assigning really, everybody is going to say, well, am I thread index 0? So, there will be 4 of them will raise their hand and they will do this work. So, what will they do? Sum equal to 0 is a temp variable, then I am going to do over all the elements of the temp and sum them up. Okay. But the work is not done here, this sum is a local sum. Now, it has to be added to get a global sum. So, atomic add C sum. So, each of this thread, those 4 thread zeros are told that you have to sum it up and you have to add this to C. So, after this C will be the answer. This one line, because each of them you are not going to do in a loop, each guy is going to go to C, and if it is free then it will add it, if it is not free then it will wait until the other thread which is trying to add is finished this work. Okay. Is that clear? This is the function which will give me C, which will be stored in global. This will be global variable inside the GPU. So, this example illustrates how to use shared memory. So, main program is very easy. So, there are of course create arrays and mem copy, all that I have skipped, because you should know that by now. That is straightforward. No, you create array, whether you can create array inside the GPU itself. Random number, there are random number creator inside GPU, but we have been following the scheme that we create in the main CPU and transfer, follow that for time being. And this is my function dot product kernel, which was there in the previous slide. And so, this is my number of blocks and this number of threads, and these are the variables dev A, dev B and dev C inside GPU. Dev A and dev B's are arrays, but dev C is not an array. Now, one question is, why my block is some crazy function like this, crazy number like this. So, it is n plus thread per block. People also write TMB. This is a quite a usually quite a generic variable, minus 1 divided by TMB. Why this? So, if n is divided evenly by TMB, then great, you can just use n by TMB. So, 64 by 16, that is fine, that works well, but what if it does not? Okay. So, imagine that I have 64 n and TMB is 16, fine, is 4. What if I have 65? Then I need an extra block, no? So, but 65 by 16 will be what? This is a integer division, it still give me 4, which is wrong, no? I mean, I need 5 blocks. So, that is why you add 64 plus, well, 65 is 65 plus 16 minus 1 is 15. Okay. So, that will be 75 80 by 16, that will be 4 5. So, yeah, that will be 5. Okay. So, this is to make sure that we have enough number of blocks if this n is not divisible by number of blocks, by thread blocks, sorry, thread blocks TMB. Okay. You can convince yourself that this will work, this will always create enough number of blocks for threads. Some will be empty, but it will create. All right. So, let us sum in array A. So, one way to do is what I showed you, right, shared memory, but there are other ways to do it. So, this is called reduce operation. The way we had reduced, we seen it before, OpenMP, MPI also reduce, you know. So, reduce can be done, but there is a nice library called Thrust library. I am not going to discuss Thrust library, but there is a pretty nice documentation, and these are fast libraries. Huh? And so, Thrust library, I am just showing you the syntax. You create a vector. Okay. So, thrust colon colon means this is using Thrust library. Okay. And it creates a data, all are 1. Okay. So, these are like one line. Is creating a vector of double and all are 1. Okay. So, these are like blids. In fact, Thrust is supposed to be doing all this vector stuff like Python, you know, one line you want to do more things. So, Thrust has that stuff, and this is for sum. So, data 1 begin to data 1 end, all the elements starting with 0. So, I could have offset already. So, this is offset, sum plus a number, we can do it in one line, and I am using the operator plus. You could also do product and logical sum, all that can be done, product, and so this is my answer, sum. So, it is one line for doing sum, and this is supposed to be efficient. In the last one I did, okay, let me finish this one. So, this is print the sum and return, and this function will run on GPU. These are for GPUs. Here the sum is not very efficient. Why is it not efficient? Because here let us say we have 1000 blocks. So, I am going to do this this atomic sum 1000 times, right, one after the other. This is okay, I think this is fast. Local sum is okay, I mean I think we are doing it within a block, it will be fast. But this is using the global variable, lot of there are communications, okay, it is hidden from you, it is talking, this compiler is doing all the work, or rather compiler has written stuff, CPU is, well, GPU is doing all the work, communication, this that. This is not very good. Why is it not very good? Because I am doing one after the other. here, then here, then here, here. The better way is to do in a tree. So, if I have 8 numbers, then I can divide into 4, then 4 can divide further into 2, 2. So, if you do it in a tree, it can be done in less steps, right. I mean, this is a common logic. So, reduce, that is why reduce, try to use the function which is built in function, do not try to do it yourself. This is a log n times in terms of complexity, and if I do like this is n, and this is the bottleneck, okay. This is the bottleneck, this will take time, though it is only adding one number, but this communication is time consuming. So, this is why I said this thrust is very useful library, but in this course I am giving you some exposure, and you can look at it if you want to optimize your code. So, let us do another one thing, which is matrix and array multiplication, which we did it in the past, y equal to x. So, how will I do it in a GPU? So, this shifted again. So, this array A is m by n matrix, my x is n and y is m, okay. It better be, right. I mean, m and n need not be equal. So, what is the idea? So, how many blocks and how many threads should I create? This is an illustration. I took the example to illustrate that. So, we want to do in such a way that multiplication is done by threads within a block, right. M and n can be large, just assume that they are large. So, I would like these operations, this multiplication operation, this versus this with that, this with this. So, that should be done by threads. So, I would like to generate n threads, right. So, there are n elements in x vector. So, n threads. How many blocks should I create? M blocks. This is a simple design. So, m blocks and n threads. So, that is where your some cleverness is useful, solve this problem. So, divide into m blocks and n threads. Okay. So, first example is there is only one thread. Okay. So, the first example is stupid. Okay. So, I am going to do the stupid example first, stupid solution, and if it is one thread each. So, it is just going to do what if I only one thread, then what should I do? I will do a loop, I will be doing a loop, right. This one will be in a loop, and loop is not very efficient, but we will just do in a loop, and that is the answer. Okay. This is not efficient. So, the function is very easy. So, you have block ID. So, by the way, I need to know which array is under my control, which part of the array. So, I is the block ID, then you can see I, so I is less than m. So, this is okay. This is just to make sure that I am not crossing the array bound, but I am doing this sum over all n, this sum over all n, right. I j less than n, j plus plus, and what I am summing? I star n plus j. What is that number? For given I, it will be in, well, for I equal to 1, it will be these numbers. So, I am working with 1D array. This is telling you that I am working with 1D array, and I am multiplying by xj and getting the sum. So, I am using a loop, and yi is sum, and yi is the result, but this is not very good. Other idea is, so this is implementation, m blocks and one thread. Okay, done. The better thing is to, as I said, n threads, use n threads per block, and you use a temporary location shared memory and sum. So, right. So, I am going to multiply, but keep it in temp memory and sum. So, these will be parallel, yi is the sum. So, this is the function. So, I create a shared array temp n. Okay. So, temp n will be the shared array, and then I do the same operation. First get the index of A, which is exactly like what I did before, block index multiplied by n plus thread index. Is it clear to all of you? yes or no. So, block index is like j for me, no sorry I for me, I block index is I. So, I star n plus thread index is j. Remember, I is it clear? To I equal to 0, it will be this one, will be just j. Next one is n plus j. So, I start with this is n, right. So, this is 0 to n minus 1, then I am starting with n is going to be 2 n minus 1, like that. Okay. So, this is what is done by inde, and a inde multiplied by this one. So, it is done for every thread is computing temp. So, this is parallel, and after that if thread is so then I do the sum. So, multiplication is parallelized, but sum is not parallelized, sum has to be done in a loop, and it is done here, and that is it. So, I am done. So, this is better function than the last one, and main function call is m comma n. Okay. So, I think I will stop here.